When I added flames and smoke to my game using Unity's particle systems, it looked great. So I did what any reasonable developer would. I turned the dial way up. I mean, how do you tell a minor deity they're allowed fire effects, but only a little bit? Unfortunately, that's where things went south, especially the frame rate. My immediate future became clear. I needed to understand particle systems well enough to extract exactly what I needed. I could then discard them and optimize for my specific use case using burst-compiled jobs. Unity has competent and useful built-in particle systems, with VFX Graph taking processing to the GPU for insane performance when rendering huge numbers of small ambient particles that do not require too much interactivity. However, for some special cases, I need the functionality of manipulating individual particles in various ways over time, depending on what happens in my environment. While it is possible to fetch particle data from Unity's built-in particle system, manipulate the data, and update the system, I kept running into performance issues at scale. So I decided to replace Unity's particle system and mirror the bits of its functionality that I need. This allowed me to integrate individual particle simulation and behavior into the rest of my dynamic environment for the entire lifetime of the particle. In this video, we will consider the different factors at play and walk through the process I followed to determine bottlenecks, understand why they occur, and ultimately resolve them. We will use wind-reactive flames and smoke as our test cases. And our possible ultimate destination surprised me, so stay tuned for that. I think this is a very nicely ring-fenced example of how to go about optimizing something, both conceptually and practically. First off, we'll consider what actually needs to be rendered. Simple billboard-type meshes, but with some nifty additions. Next, we look at the flow of information from CPU to GPU, and how our shaders need to change to handle GPU instancing. Then we run through the actual particle system and how it creates, simulates, renders, and removes particles. This brings with it some technical challenges that require creative problem solving to resolve. Finally, we'll identify possible future optimizations. In terms of meshes, Unity's particle system allows you to specify complex meshes, but most particles are usually rendered as a simple quad mesh, or two triangles created from 4 vertices. We will use this simple mesh for our smoke, but there is something we can do to make it look better. Usually, the normals of the vertices would point straight outward, perpendicular to the quad plane. In a lit shader, this means the light direction is the same for all points on the quad surface. But we could also calculate the direction of each vertex from the pivot point or center of the mesh and blend it with the straight outward normal to create a fake spherical look, with a blending parameter determining the amount of fake sphere smoothness. In Unity's particle system, you can set this blend parameter as the normal direction in the renderer component. I've written a script that creates such quad meshes with the desired normal configuration. Here are 2 smoke particles with the exact same frame and size progression. The one on the left has flat plane normals, while the one on the right has a 50% sphere normal weight. The effect is quite subtle in such a transparent particle, so here I've adjusted the shader to give us some more contrast, and visualize the smoke based on the final normals. It is now clear that the smoke with sphere normals has more contrast between the different corners, like light reflecting off of a curved surface rather than a flat plane, making it look more volumetric. If we now place these smoke particles on the map, they complement the flames well. However, these unwanted flickering artifacts spoil the party. This took me a while to finally figure out, so I originally put it on my to-do list eventually and continued. It turned out to be a crucial factor in terms of performance, which required some creative problem solving to overcome. But we'll get back to it when we look at how we send data to the GPU. Let's first consider another special case for the meshes. This is a normal quad mesh, with the UVs cycling through a texture sheet containing 64 frames every 2 seconds, exactly like we can set it up in a Unity particle system. The texture sheet is from Nature Manufacture's Fire and Smoke asset, which I bought as part of a bargain bundle. I've learned a great deal during the last year or so from just digging into how their assets work and tinkering with them to adjust them for my use. Their fire and smoke shaders apply their global wind movements to the flames and smoke, which I exaggerate here to make the point. We can add good overall movement to the flame with a quad, but if we rather create a 4x4 square grid, the individual vertices can be altered slightly differently by the gusts and shivers in the wind, to give much more life to the flames. Consider this scene where the smoke and flames are not wind reactive, and how much better it looks when everything reacts to the same global wind. We'll get to the irritating flickering. Focus on the movement for now. My mesh creator also caters for this kind of mesh, letting you specify the grid dimensions. However, this does mean our flame mesh now has 25 vertices instead of 4, which is more taxing on the GPU. For this reason, I also create 2 extra level of detail versions, by halving the X and Y grid size each time, until we end up with the original quad for the last LOD. That takes care of the meshes for now. Let's see what data we need to send to the GPU and how we send it. First off, let's consider the vertices and their UVs. A Unity particle system that is not set to the GPU instancing option actually creates a single large mesh combining all its particle instances every frame. The per particle vertices in this mesh have corresponding per particle UVs to handle cycling through the texture sheet to create the per particle animations. In addition, the particle's color over lifetime and a range of other possible values can be added to each vertex of the mesh for the shader to use. This becomes an enormous task as the particle count increases. Here's a scene with 50,000 flames of 3 different sizes handled by 3 standard Unity particle systems, not set to GPU instancing. We use one particle system to emit all instances of a flame size, since we don't want hundreds of separate particle systems to manage. We are running at below 25 FPS and barely get any FPS increase if we switch off almost all other rendering. Furthermore, if even a single particle of a system is in view, it creates the entire mesh for all the particles. So, even with only a few flames in view, the CPU is completely bogged down creating these large combined meshes. This frame rate is not practically viable. We will have to use GPU instancing via indirect rendering to speed things up. We'll consider how to achieve this next, but let's have a quick look at the speeds we can reach to give you some motivation to keep watching. When we switch the exact same scene and spawning characteristics over to our manual GPU instance particle system, we get around 170 FPS, even with almost all of the particles visible when rendering particles only, and still over 60 FPS when adding all the other rendering back in. Also, when only a few flames are visible, we pay a much lower price for rendering them only. Let's see how we can accomplish this. The first thing we have to change is that we are only allowed a simple single mesh. Recall that we're using the quad mesh, or in the flame case the 25 vertex 4x4 quad mesh as our rendering mesh. We cannot alter the vertex data for every individual particle, since we don't create vertex data for every particle anymore. Instead, we need to send the required per particle information through to the shader in graphics buffers. It may sound like more work, but it's actually less work, since we now send the data through only once per particle. For example, we can send the current color over lifetime value of a particle over as a single color value, where previously it was written to the vertex color of every vertex of the particle in the combined mesh, so 25 times for the best LOD of the Wind-Reactive mesh. So we save on the 24 copies of the color. Let's look at everything the particle system added to the mesh and how we convert that to GPU instancing mode. Depending on our particle shader, you can specify a bunch of data the particle system needs to add onto the custom vertex streams of the mesh it creates. For example, you can see that our flame shader requires the position to know where the particle should be placed, the color to adjust the particle color to a combination of start color and color over lifetime, the UVs to know which animation frame to render, the pivot point of the particle and its size. These values are packed into the mesh vertex data using the position, color and 2 texture coordinate channels as indicated. On the shader side, the vertex shader reads these values and applies the wind displacement, while the surface shader uses some of the values to determine the frame to render and apply color and transparency overlays. This shader still takes the one combined mesh from the particle system as input. We now need to convert it to a GPU instanced version. Luckily, that's not very difficult, especially if you've already struggled through it because it was difficult originally. First off, we need to add these statements to make the shader GPU instanced. In the setup indirect code, we cater for different scenarios, but the one we are interested in at the moment is our particles case. We create a structured buffer for all the required data per particle and set up the instance ID and an object to world matrix per particle so that the shader knows where in world space the particle should be rendered. Now in the vertex shader, we have to define a vertex input struct referencing only the required channels. And finally on the GPU side, we now use the particle data structured buffer rather than custom vertex streams of the mesh. and we're done. On the CPU side, we need to populate the structured buffer and call the indirect rendering. It turns out we can use lock buffer for write and unlock buffer after write to get a reference to the GPU memory of a buffer and edit it directly from within parallel jobs, rather than filling a buffer on the CPU and sending it through via the usual setData call. But there is a catch. If the CPU starts editing the GPU buffer while the GPU is still rendering the previous frame, you get race conditions leading to corrupted rendering. So we implement triple buffering to prevent this. Triple buffering takes up a bit more memory, but it allows the CPU to start populating the current frame while the GPU renders the completed previous frame. If the CPU manages to complete the current frame before the GPU has completed rendering the previous one, the CPU can even start populating the next frame as well in the third buffer without causing race conditions. I've created a triple buffer class for a generic struct, and it simply creates a 3-element array of buffers, plus a 3-element array of buffers for the indirect rendering arguments. Now, each time a buffer is needed, we cycle through the buffer index, prepare the next buffer in the array for writing, and populate that buffer, looping back to the start when we reach the end of the array. After populating the buffer, we commit the changes, and when we run the indirect render call, we tell the render parameters which of the buffers to use for the current frame. In terms of rendering, the only outstanding step at this point is actually populating the buffers. Of course, our particle system needs to be operational before we can do this. We need to be able to add particles, simulate them throughout their lifetimes, and remove them when their time is up. Also, for each frame, we need to render the ones that are currently in view. Remember that we use one particle system to emit one particle type over the entire map at many different locations. We have a useful hex grid underlying our map, so it makes sense to manage the emission locations using this hex grid. Each particle system keeps a list of hexes on which particles should be emitted, as well as a spawning interval specifying the time between spawns. Of course, we could cater for burst emissions and other variations, but for now we only need a simple constant spawn rate over time. To add particles, we implement the job on a single worker thread, with each system using one worker thread. In the job, we advance each spawning hexes interval and spawn the number of particles dictated by how much time has passed since the last emission on this hex. Note that we also have some random numbers per particle, which allows us to always make the same choices for a particle throughout its lifetime. For example, each particle picks a value between two curves for size over lifetime, and we need to save that selection. Since we can have thousands of hexes or locations at which particles are being emitted, we don't want to progress all of them every frame and check whether they need to emit. So we have a bit of admin outside the job to determine the range of spawning hexes the current frame should consider. This smooths out the emission cost over many frames. To emit a particle, we add a new entry into the list of particle CPU data structs, which contains all the information we need for simulating the lifetime of the particle. You may have noticed a 3x4 matrix in there rather than the usual 4x4 matrix. That's due to some further optimization that we'll get to a bit later. In terms of simulation, I should mention that my particle system does not cater for nearly as much functionality as Unity's particle system. But I also don't need all of that. Lifetime, size, color, and some upward movement is enough for now. I can keep adding functionality onto it as the need arises. In the simulation step, we increase the age of the particle and check whether it has reached the end of its lifetime and should be removed. Note that we use pointers to the data to allow us to directly alter the native array memory without having to assign new structs to the memory. This gives us slightly better performance. Now, as the age advances and the camera's position changes, we need to update the frame, position, size, rotation, etc. of the particle. However, we only need to do this if the particle will be rendered. In the video in the top right, I described how I already cull each hex in the grid. We can now use that information to cull our particles as well, since each one is located on a specific hex. This saves us the simulation effort for out-of-view particles, assuming that it's not important for them to keep changing while they are out of view. While we're at it, we also populate a native parallel multi-hash map indicating which frame and which LOD each visible particle should be rendered as. This is a good time to mention that when creating the quad meshes, we create a combined mesh containing a copy of the mesh for each UV frame of the texture sheet for each of the LODs. If we now keep track of the vertex index at which each frame of each LOD starts, We can create one set of render arguments to tell the shader which frames to render in a single instanced render call. I also covered this technique in a previous video. For this reason, I'm not going to go into the detail of the next two jobs. The first one collates all the instances that have been identified as in view and counts how many there are per LOD and frame combination. The second one populates the render arguments by writing these counts, the start indices, and the number of vertices into the arguments buffer per LOD and frame. Note that we populate a buffer containing entries for a particle shader data struct that aligns with the struct on the GPU side of the shader, although we have also added a local wind speed multiplier since we last saw it, and now send only the first 3 rows of the transformation matrix through, adding the constant 4th row in the shader. When it's time to remove particles, we sort them and start removing from the last entry, so that we can use remove swap at back to just slot the last non-removed entry into the slot that removing an entry creates. This means we don't have to keep track of unused slots in the array. So that was a bit of a code overload. Let's get back to some visuals. Applying all of this for the flames works really well, and it looks good, especially when the wind reaction also comes into play, as seen on the left. Also note the subtle, fake light reflections I've added to the buildings, trees, foliage, and ground to further sell the fire story. But when we apply this to the smoke, we get this irritating flickering. Why is that? Well, the flames are rendered with an unlit shader with emission, since the flames act as light sources. Also, the flames don't really overlap. However, the smoke uses a lit shader, and they do overlap significantly. For transparent particles like these, the order in which they are rendered causes a difference in the final visual result. When we determine which particles are visible, it happens on different parallel threads, with no way of keeping the order in which they are added to the render list constant. The GPU renders them in the order that they are added to the render arguments, without sorting them based on their on-screen depth. The flickering is due to this order changing randomly every frame. We are going to have to sort them by distance to the camera. Unfortunately, this means we need a fairly large change to how we've been handling the UV frames up to now. Currently, we write all frame and particle combinations into a hash map, with frame as the key. In essence, our rendering order is sorted by frame, rather than distance to camera. We need to get rid of all frame-based workings and replace them with a LOD and distance-based system. In terms of the mesh, we still create one mesh copy for each LOD, but we don't create different copies for each frame anymore. Instead, we use only the UVs of the first frame for the mesh. If we also send the current frame data to the shader and give the shader the texture sheet's dimensions, it is trivial to simply slide the UVs along on the X and Y plane to take care of the animations in the shader. So that's easily sorted. What isn't as easily sorted is the sorting. But after about a day's work, I managed to design and implement what I think is a very nifty solution. Ideally, we would like to be able to handle tens of thousands of visible smoke particles on a large map, let's say 40,000 to be excessive. I knew from the start that sorting an array of 40,000 particles every frame would turn out to be problematic, especially if you have to do it 2 or 3 times for different types of particles. So I ran some tests to see how bad the situation was. Efficient sorting algorithms are generally of order n log n when all goes well, and up to n squared in worst case scenarios, where n is the number of particles. This table summarizes a few simple tests I performed. On average, it took almost 12 milliseconds to sort 40,000 elements. Since you only have 16.7 milliseconds per frame available to do everything you want to, if you're targeting 60 FPS, this is a dire situation. But with a combination of tricks, there is hope. First off, the higher the order of complexity, the more time you save if you are able to break the sorting up into a few smaller buckets. For example, to sort 8 buckets of 5,000 elements each should theoretically take 80% of the time it would take to sort one bucket with 40,000 elements, if the sorting complexity is n log n. For n squared complexity, this becomes only 13%. I ran some empirical tests and found that it took only about a third of the time to sort 8 buckets of 5,000 elements compared to one 40,000 element bucket, and just over 40% of the time for 4 buckets of 10,000 elements each. Of course, this is only helpful if we can ensure that each bucket contains only larger elements than the bucket before it. since you can then simply append all the smaller buckets to get 40,000 sorted elements. Luckily, there is a way to do this. We force the particle system to have 4 LODs, even if the mesh is the same quad for the 4 LODs. Then, when we perform the culling of the particles, we determine how far each particle is from the camera, and place each particle into one of the 4 LODs based on this distance. Now, before transferring the visible particles' data to the graphics buffers, we first sort the entries of the 4 LODs separately by distance to camera, then add them to the graphics buffers in reverse order so that the furthest particles are rendered first. This allows us to render about 2.5 times as many particles for the same cost in terms of sorting. Finally, we only sort if it is actually required. As we've seen before, we don't have to sort the flames at all. Also, since the worst LOD is far away, the flickering is almost unnoticeable for it, so we choose to also keep that bucket unsorted to further increase performance. But we can do even more. There is an old saying that goes, the cheapest polygon is the one you don't render. We can expand this to any kind of processing. I've added a thinning out parameter to the particle system. It merely starts randomly discarding visible particles from a certain distance, based on one of their fixed random numbers, so that the same ones are discarded each time, thinning out more and more the further the particles get. This also helps give a smoother transition on the visibility edge, rather than everything popping out at once. I've added a particle quality slider and visibility toggle to my graphics settings that adjusts the number and quality of visible particles, so players can tweak this depending on the power under their saddles. We can see here that a combined flame and smoke particle count of 130,000, while starting to become taxing, is still very viable, which means more reasonable use will be smooth and fairly fast. In terms of future work, I still want to explore making the particles wider, maybe 2 frames next to each other in one particle when they are further away, so that we need even fewer particles to cover the same ground. Secondly, particles are currently rotated towards the camera on the CPU, and the entire translation matrix is synced to the GPU. It's possible to send only the positions through and perform the rotation per vertex on the GPU. It would be good to test which approach works better in our case. A final approach I want to test is to handle particles the same way I currently handle the dense foliage. Instead of always having particles in memory, simulating them constantly and culling the ones that are not visible, I want to try and create at least large amounts of cosmetic visible particles every frame, depending on what's in view. For this to work, a particle needs to be completely deterministic from only the lifetime of the particle. We will have to sacrifice some true randomness over time scenarios, but for our use case that's not an issue. This will be a fairly complex endeavor, so for now let's call it a day and play out with an example of just how much control I now have over each particle. If we pour rain showers out over a patch of burning terrain, having the existing flames react to the rain immediately, rather than simply stopping the addition of new particles and letting the existing ones run out their lifetimes normally for up to 16 seconds, adds a lot of immersion. And since most of my structures are already data-oriented, I can pull any of them into the jobs and base the particles' visual rules on them, from climate and elevation to roads and floor plans and so much more. And that's it for this video. It was fascinating to learn about the intricate details of particle systems, and I hope you enjoyed and learned from my journey too. Please like if you enjoyed the video, leave a comment, subscribe to this channel, wishlist and follow Minor Deity on Steam, or join the Discord server to stay up to date. All the links are down below. Also, feel free to ask specific questions you may have. Thanks for your time and support.